And good morning, everybody. Here are your notes for exponential growth and exponential decay, and we're going to do some word problems on IXL.com module X.5. But before we get into the problems, let's go ahead and talk about the basic structure of an exponential function. So just like when you studied linear functions, y equals mx plus b, there were certain things you could tell just by looking at the equation. So for example, if you had a equation, a linear function, so a linear function, y equals mx plus b, after studying this equation, you automatically knew that this value here was going to be the slope, or the rate of change, and you knew this value here was going to be the y-intercept, or the initial value. So if you were to graph a equation, let's say y equals 3x plus 1, just by looking at the equation, you would know that the graph of this, you'd have a start value of 1 on the y-axis, and then you're going to have a slope of up 3 and over 1. So you're going to go up 3 over 1, and that would be enough information just from looking at the equation to make a quick graph of y equals mx plus b, or in this case y equals 3x plus 1. So what we'll do before we start the word problems is we'll look at the basic form of a exponential function and talk about the different parts and pieces of that function. So the general form for a exponential function, we're going to say it's going to be y equals a multiplied by some base to the x power, and a is going to be the initial value, or the y-intercept, and the reason for that, if we think about when we're on the y-axis, if you're on the y-axis, your x value is going to be 0. So if your x value is 0, you would end up with y equals a times b to the 0 power, and we learned that anything to the 0 power is 1. So your y value would just be whatever a is when x is 0. So that would get you your initial start value, whatever that a value is. So that's going to be your a value, and then the b is going to be your growth factor. Or your decay factor. So that's what's going to be multiplied against the initial a value each time. So for example, if we looked at a equation, let's look at y equals 5, and let's say our b value is 3 to the x power. So your start value, whatever it is that you're working with, your initial start value when x is 0 is 5, and then they're going to take the number 5 and multiply it by 3 a certain number of times depending on what the power is. So let's make some room here. So let's say, for example, we were dealing with this equation. Let's just work with this one here. So, for example, if x was 0, then you're going to get y equals 5 times 3 to the 0 power. And 3 to the 0 power, we know that's 1, so you're going to get y equals 5. So that's going to be your y-intercept. And if we chose another x value, let's say x equals 1, you're going to get y equals 5 times 3 to the first power. So it's going to be 5 times 3, which is 15. And if x was 2, then you're going to get y equals 5 times 3 to the second power. So y equals 5 times 3 times 3. So again, the 5 is the initial start value, and the b in the equation is your growth factor, how many times you are increasing that value by, so the factor that you're increasing it by. So notice it was increased by 3 times another 3. So that's going to get you 9 times the 5, so that's going to get you 45. And you can kind of see that exponential growth pattern that we were talking about the other day. So notice to get from here to here, we had to do times 3, and then go from here to here, you had to do times another 3. And your function is going to grow rather quickly. So it's going to have an initial start value on the graph of 5, and then it's going to show that exponential growth and kind of go off the chart really quick. So it's going to grow really fast, and then it's going to approach the x-axis, but never actually quite reach the x-axis. You're just going to get really, really, really small fractions that are traveling right along the x-axis. And let's just go ahead and look at some common forms that you're going to see this general form come in. So here are a few common forms. So we have the basic algebraic y equals a b to the x, where again the a is the initial value. And b is the growth or decay factor. Another common form might be when you are needing to work with percentages. So someone might not tell you that something is doubling or tripling or being cut in half each time. Someone might say that it's increasing by 5% or 10% or 20%. So to determine your growth factor when you're given a percent, then it's going to be the same basic form. It's going to be y equals, you're going to have a start value, but to determine the b, the base, it's going to be 1 plus or minus whatever your percent rate is as a decimal, raised to, again, whatever the power is. So the 1 plus or minus r is basically making the b value for you. And r in this case is going to be the percent growth or decay. And it's going to be as a decimal. So if it was 5% growth, so for example, if it was 5% growth, then 5% as a decimal, move the decimal 2 spots to the left. So it's going to be 0.05. And if we put that into our equation, it's going to be 1, since it's growth in this case, this example, since we're doing growth, it's going to be plus the r. If it was decay, it would be minus the r. So it's going to be plus 0.05 for the rate to the x power. And then once you have your percent rate plugged in, you can go ahead and simplify that base value. So 1 plus 0.05 should get you a base of 1.05. So that's going to be your growth factor. So if you're given a percent, then you'll just need to work through using that rate to create the b value or the base for that particular equation. So this is still the base. This is the base. This is the base. This is the base. This is the base. So this is all still the base or the growth or decay factor, and this is still the initial value. So whatever value you are starting with. And just one more common form you might see, especially when you're dealing with finance a lot, is it's kind of the same model. They just have different variables to represent certain things when you're dealing with interest and compound interest. So if we still look at the basic general form, y equals a, the start value, b, the growth factor, to the x. You might often see a formula that looks like this, where a is replacing your y, capital P is replacing your a, and then for your base, your growth factor, it's going to be 1 plus the interest rate raised to the t. So it's still following the same form. This is still your start value. They call that the principal, the amount of money you're starting with. This is still your growth factor, your base. So it's going to be 1 plus. Since we're assuming the money is growing at a certain interest rate, then it's going to be 1 plus. I guess if your money was decaying, if you're losing money, you could put in a minus r there. So if it was losing money, you could maybe put in a minus r. And then the t is the x value. So you still have your x value here. So a is standing for the amount. And we're usually talking money if you're using this equation. So that's your final amount of money. P is your initial amount of money, or your principal. So your starting money. And the 1 plus R is still the growth or decay. So that's the 1 plus or minus R. And T is standing in for time. Alright, so knowing all that, let's go ahead and try some of the word problems that you are going to see on IXL.com Algebra 1, Module X.5. So here's the first word problem. It says Tess has $70 in a savings account, so that's going to be her start value. So she's starting with $70. The interest rate is going to be 10%, so we're going to be thinking about this as a R value, 10%. Compounded once a year, so annual is once a year. To the nearest cent, how much money will she earn in 2 years? So she's starting with 70. Her money is going to grow at 10%, and it's going to be compounded annually, and they want to know how much interest she has after 2 years. So let's go ahead and set this up so we can go ahead and say that we can just use the Y value. What was her starting amount? 70. What is her base? That's going to be 1 plus the R, so R at 10% as a decimal is going to be, let's clean that up. So R as a decimal is going to be 0.1. So it's going to be 1 plus 0.1. And we're doing plus because it's growing. And then we can say T or X will be the number of years. So Y equals 70. It's going to be 1.1 to the T. And what's T? How many years? 2. And then on a calculator you can evaluate this. So on a calculator you want to do 1.1 to the second power first, following your order of operations, then multiply it by the 70. So you should get a final value after 2 years of $84.70. The trick on this one is they want to know how much interest did she earn. So this is how much money she has in her account, but remember she started with 70. So if we minus 70, that will tell us how much interest or how much difference she has in her account, so how much she actually earned. So if you subtract that, you should get $14.70. So $14.70 should be going into the answer box. And let's look at the next one. So Jacob has $20 in a savings account, so that's going to be his start value. The interest rate is 10% again, so R as a decimal will be 0.1. Compounded annually to the nearest cent, how much will he have in 2 years? So we'll say Y is going to be, how much is he starting with? $20. What is his growth factor? It's going to be 1 plus the interest rate. So 1 plus the R value, 0.1, to the T or to the X. So Y equals 20. We'll simplify the 1 plus 0.1 and call it 1.1. And how long is it going to go for? What's his time? 2 years. And you can work that out on a calculator. Do 1.1 to the second power, then multiply it by 20. Make sure you remember to follow PEMDAS, your order of operations. So you need to do exponents first, and then you can do the multiplying. So 1.1 to the second times 20, and you should get $24.20. And that's going to go into the answer box. So the difference between this question and the last question they wanted to know how much interest did she earn over those 2 years. This one they just wanted to know how much money will Jacob have in his account. So he started with $20 and he ends up with $24.20. And here's the next one. Says you have 96 grams of radioactive kind of indium how much will be left after 6 days if its half-life is 3 days. So we're starting with 96 grams. This one's going to, let's see, it looks like it's decaying. So a half-life means that it's being cut in half each time. So our start value will be 96. And we're not going to multiply it by a growth factor, we're going to multiply it by a fraction. It's going to get multiplied by a half for every half-life or every cycle that it goes through. And then we're going to need time. The trick for the t-value on this is they said its half-life is every 3 days. So it's not going to be cut in half until t becomes 3. So t would have to equal 3 days. So t wouldn't actually be 3 itself, so this is a little tricky. If t was 1, if you use this definition for t, if t was 1, then that would equal 1 3-day cycle. So what you'll see a lot of people do is they will actually divide it by 3. And now you can have t, so instead of using this definition for t, now you can say t is equal to 1 day. That way when you get to your 3rd day, when t is actually 3 days, notice if you put the 3 in for t, you get 3 divided by 3, which is 1, which is 1 half-life. So that's going to be 1 cycle. So we'll say y equals 96. You have a half-life, so you're cutting it in half. They want you to go for 6 days, so it's going to be 6 over 3. And notice if you simplify that fraction, 6 over 3, you get 2. Which should make sense because 2 is how many half-lives it's gone through for 6 days. So if its half-life is every 3 days, then 3 days and 3 days it's gone through 2 half-lives. So we can work that. So a half times a half, that's going to get you a 4th. So you want to do 1/2 squared, and that's going to get you a 4th. So 96 divided by 4 should get you 24, and that's going to be grams. So 24 grams is the answer, and that should go into the answer box. So after 2 half-lives, it's going to be down to 24 grams. And looking at the next word problem. So Janet has $700 in a savings account. She's going to earn 1% interest. So R, your rate as a decimal, is going to be 0.01. So remember, if you have 1%, your decimal is here. So you're going to go 2 spots to get the decimal form. So R is going to be 0.01. It's compounded annually, and to the nearest cent, how much money will she have after 3 years? So the amount she has, Y, you're going to start at 700. It's going to be 1 plus the R value, which is 0.01, raised to the time, or the X. And you can simplify your growth factor. So 1 plus 0.01, that should get you 1.01. And we're going to go for 3 years. And you can work that out on a calculator. Do 1.01 to the 3rd power multiplied by 700. So you should get, rounded to the nearest cent, looks like $721.21. And that should go into the answer box. And I think we have one more. Says Allenville High School has student elections every year. Lately the school has seen a 10% decrease, so this one's a little different. This one's going to be going down by 10%, so it's going to be a minus R situation in voting from election to election. If 868 students voted this year, how many will be expected to vote 5 years from now? So the start value is going to be 868. And it's going to be 1 minus the rate, so it's going down at 10%, so R is a decimal, is going to be 0.1. And the number of years, so y equals 868 is the start value. It's going to be 1 minus 0.1, which is going to leave you with 0.9, which, if you think about it, is kind of another way to think of this. If you're losing 10% every year, then you're left with 90% of what you had. So 0.9 is representing that 90% that you're left with. And we're going to go for 5 years. So 5 years. And then you can work that on a calculator. You can do 0.9 raised to the 5th power, multiply it by 868, and you should get about 513 if you round it to the nearest whole number. So that's going to be your final answer. And that is the end of the notes and the examples for this module. So again, this is the exponential growth and decay models, the word problems, Algebra 1, X.5. Thank you. Have a good day.